Good evening, everyone. It's Thursday night, so it must be time to do a cross-country intro to cross-country seminar. Tonight's topic is model-based weather forecasting. The so as we kick this off, so here's our schedule. Tonight we've got the model-based weather forecasting. In 2 weeks, we'll talk about flight tracking. And then we'll finish up the first part of May with discussion about online contest and WeGlide and those kind of things. So the material is available. It'll be available early next week, probably on the SSA website. And so here's your instructions on where to find both the slides and the recording. Our webinar, the SSA provides the software, and Frank hides in the background to keep this thing running for us, so we really appreciate that. Wings credit. So we have several members of our club that are on the FAA safety team, and these are the folks that get all the paperwork done so that we can offer wings credit for the folks that are attending the class in real time. If you registered for the seminar with your Wings user ID, the credit will be applied automatically over the next few days. If you don't see that you've gotten credit after maybe a week, send me an email and we'll see what happened. You know, chances are you used a different email to register with. The FAA has guidelines on that allow online seminars to count for Wings credit. Only the live seminar is eligible, and you've got to be in this seminar, in the live seminar, for at least an hour. We have some of our club instructors hiding in the background this evening, and their job is that, you know, if you send them questions, they'll answer them. If they're larger, broader interest, then we'll collect them and address them at the end of the presentation. So this evening, on the left of this slide is a skew T generated from a radiosonde. So temperature, dew point, wind direction, velocity, all plotted for altitude. That's the kind of tools that we used to have to use before we came up, you know, before the people developed the models that we use today for our weather forecasting. And on the right is the depiction of the geostationary operational environmental satellite. The short name for it is GOES, and that's the field of view for the two satellites that are on orbit that monitor most of the Western Hemisphere. Acknowledgements. An awful lot of people have contributed to this over the years, but Dr. Jack Glendenning did an awful lot of the work that turned our charts and graphs, you know, something of a science project that we all played with on Friday night, trying to look into Saturday morning, and came up with a way to visualize this and make it easier for us to understand. For instance, Dave Leonard, our local RASP expert, took the Dr. Jack's work when he put it out as regional processing and made it available for the Front Range of Colorado. And these days, everybody's aware of Matthew Scudder's SkySight forecast tool, which took some of Dr. Jack's work, added some other work, and has taken this soaring forecast products from a local or regional level out to a worldwide product. So tonight we're going to describe the tools and then I'll do a SkySight demo. Weather observations, you know, sometimes we wonder where all of this comes from. Going all the way back to 1870, that marks the beginning of the official weather observation in the United States. And you can see the various dates. By 1914, it was decided that, gee, we needed to do something for aviation. By 1926, they formalized the Weather Bureau and said you will provide services for civilian aviation. By 1937, the first of the radiosonde type of devices were starting to be used. In 1942, the Navy transferred 25 surplus aircraft radars to the Weather Bureau. They were modified to be used for ground meteorological use. So this was the very beginning of the first of the weather radars. In 1960, the world's first weather satellite, it was a polar orbiting called Tyros. Um, and we're now up to the NOAA, or the satellites for the polar birds are called NOAA dash and a flight number. We're up to Bird 21, went live in 2023, and Bird 22 will launch in 2027. So that gives a polar orbit weather satellite. And then the GOES satellites, they were started as a hurricane hunter satellite. The first of them went up in 1975, and GOES 19 uh, went live in 2025, and there are two of those birds on orbit plus a couple of live backup spares. In 1989 was the first of the AWOS stations, and 1991 was the first of the ASOS stations. So this has been a growing endeavor in measuring the weather for us, measuring, what happens every day kind of thing. Our National Weather Service, it's weather, water, climate data, forecasts, warnings. So the whole thing is to protect life and property and enhance the nation's economy. They produce a lot of aviation products, but they also, they're working in a different problem space than just soaring forecasts. Fortunately, there's a bunch of weather scientists that work at that also are soaring pilots, and so they've adapted and evolved the National Weather Service tools and the processing techniques to give us, the foundation and the underlying information to do the processing with our weather models. So there are a lot of things that get depicted, advisories, watches, and warnings. For instance, this map is showing fire warnings, high danger, high winds, high wind warnings, that kind of thing, all the way out onto the coastal area for weather out there. For aviation, we get the prog charts, especially if you've got a power license. You went through a whole little weather course so that you could read these for your license. And then we have the weather observations from all over the country that also contain warnings and areas of interest for significant weather. When it comes to weather modeling, um, the first of the what's held as the first of the models came out in 1948. What happened is in March 20th of 1948, a major tornado hit Tinker Air Force Base. It damaged or destroyed 54 aircraft, bunch of buildings. There were 8 injuries, and fortunately, there were no deaths. Commander uh, came up to his weather people and said, "We've got to come up with something to do to, predict this, because tornadoes are a fast-acting, short-lived phenomenon. So how could we tell?" Well, the two gentlemen listed on the plaque here, Major Fallbush and Captain Miller, were tasked to come up with something that would help them to forecast tornadoes. In 5 days, of course, they were working around the clock, and you know, anyway, they came up with what they felt was a method. They came up with a model that they thought would help them predict tornadoes. And 5 days later, on March 25th, they used their technique to provide a warning to the base to help secure operational aircraft and move personnel to safe locations. The second storm tracked within 100 yards of the earlier storm. It did damage or destroy an additional 84 aircraft and a number of buildings, but there were no injuries and no deaths. The real thing is, the really important thing is that they created it wasn't a computer model. It was, they had to do a lot of the work in the background, or they had to do all of the work in the background, but they created a model and they accurately predicted the tornado and its path. Today, our forecasters are using models for that derive both from direct measurement and remote sensing observations. So our modern models are using both types of observations to initialize the models, and then uh, what they're attempting to do is extrapolate this out for areas that don't have direct measurement observations. We've got areas in the country that we don't get direct measures from. And then with the large data sets that they've derived, they've been able to use this information to gain other insights into larger scale phenomenon that are too large to be seen just by looking at local data. What it boils down to is with weather modeling at the National Weather Service level, we predict storms locations, and then you have to validate what the model tells you. So then we can observe its physical formation and the intensity and feed that back in with the whole idea of to provide an increased warning. So a couple of definitions when we start talking about modeling for flying gliders. The first one is the boundary layer. This is the active thermal layer of the atmosphere. It's generally 1 to 4 kilometers thick, so somewhere between 3,000 and 13,000 foot thick. This resides inside the planetary boundary layer. So this is where the effects of friction between the atmosphere and the Earth are significant. It doesn't mean that the convective activity stops at the top. So on the planetary boundary layer is roughly the 1 or 2 kilometers, the lowest 1 or 2 kilometers of the atmosphere. But notice I said this goes up to, somewhere in the neighborhood of 4 kilometers. So, but this lower part is where the temperatures are most strongly affected by the daytime heating and the nighttime radiational cooling. Winds are usually affected by the friction. And so the effects of this friction die out gradually with the increased height. So the top of this layer is, the top of any of these layers is kind of wishy-washy. It's kind of soft. It's not a firm boundary. And then hiding underneath all of this stuff in the boundary layer is what's called the surface layer. And this is where the friction effects from the wind is more or less constant as opposed to decreasing. Now, it's interesting because the surface layer is only about 10 meters thick. So that's why the AWAS towers and the ASOS towers have a tower that they take the wind measurement at 10 meters above the ground. And then there's another measurement that you'll often see so that's the surface boundary layer winds. And then there's another one where they also take wind measurements at about 2 meters above the ground. When we look at the models, especially at the National Weather Service level, which is the background processing for all of our soaring models, there's a synoptic scale. So synoptic is huge. This refers to a large scale, or they call it a cyclonic scale. So weather patterns from anywhere about 1,000 kilometers or 600 miles to 1,500 miles or 2,500 kilometers. Okay. The next one down is the mesoscale. These are referring to weather systems that are smaller than synoptic, but larger than storm scale systems. Okay. Notice that the size boundaries are kind of fuzzy. Anyway, in the mesoscale, it's generally from, somewhere around 50 miles to several hundred miles. And then we get down to the microscale. So this is basically what they refer to as storm scale. So the size of a thunderstorm or the size of a hurricane, somewhere between those two. So that could be anything from, 5 miles to several hundred miles. Mesoscale models are usually pretty good out to 3 to 5 days. Microscale models usually break down uh, somewhere around 3 days. And the soaring models are working generally somewhere between the microscale and the mesoscale models. Basically, our weather models are initialized from direct measurements, surface measurements, atmospheric measurements via instruments, and remote observations. So this is, coming from the Earth observing satellite instruments. The numeric weather models, they predict a behavior. The different models, there are a number of different models. They're targeted at different phenomena, so they're looking for different behavior. but the output of these models can be used as building blocks. Interestingly enough, that the models can be cascaded. The key, though, is that once you've got the results from the models, they have to be interpreted against the intended use. In other words, like our soaring models, we get it out, but we have to interpret it against a planned or, a theoretical flight. So the models are an abstract of reality. I've talked about this before. It can be anywhere from a single expert to a group of experts. It can be manual, it can be automated, it can be a mix. But again, they always have to be evaluated for suitability. So every time there's significant weather, the model predicted it, the actual is measured, and then those results are fed back to the research folks to be sure that the models are actually, giving us the results that are adequate for our needs. When we're looking at direct measurement, so this is where the phenomenon can be actively and directly measured. We can start measuring with the NexRad radar sites. So, generally we can get down to 10,000 feet AGL. There's 160 locations across the country. In clear air mode, so there's no active weather out there. The images are updated about once every 10 minutes. In participation mode, so when we've got a storm coming or there's storms active, the images are updated every 5 or 6 minutes. Basically, the whole idea behind this is local severe storm characterization. This is the radar that you see, that the local TV stations put on the nightly weather. Then we have the Raytheon sites. So these are the balloons that go up. And so its position is tracked as it ascends to give wind speed and direction information, temperature information. Some of them can carry their own navigation devices. Others have a radar reflector on them. This is a direct measurement of the atmosphere. The colors on the chart indicates the organization that owns the particular site. So there's the red ones, the red triangles are the Global Climate Observing System, and the blue dots are the Upper Air Program under National Weather. Okay, other direct measurements include ground measurement observation sites, so the automatic surface observation stations and the automated weather observation stations. We're used to thinking of, AWOS is what we talk to or what we hear when we, at our local airports. The difference between AWOS and ASOS is generally ASOS is predominantly used for severe weather detection, whereas AWOS is generally associated with aviation. Okay. In Colorado, so I'm showing a map of Colorado. The blue markers on there are the Mountain AWOS program. The Colorado Department of Transportation has put AWOS stations out into the mountains for us, for the aviation people. The yellow markers are general aviation airports with either AWOS or ASOS. The red markers are commercial airports with AWOS or ASOS. And the purple markers are private airports with AWOS. And if I remember correctly, the only private one is the Meadow Lake Airport. Remote sensing. Remote sensing from our satellites. So this was the GOES-R satellite, so turned into GOES-16 once she was on orbit and checked out. Being worked at, here's the solar array that was in a clean room at Lockheed Martin in Littleton, Colorado. So these are geostationary satellites. They set out over the equator, somewhere between 35 and 40,000 kilometers out. The imager on this satellite, the primary imager, has 16 spectral bands. So, it's not just visible. It's got 2 visible channels, 4 near infrared channels, and 10 infrared channels. And it's looking at all different kinds of things. And then it also has other terrestrial and space weather. For instance, I'll show you a video here in just a second. It has a lightning detector, which is one of the things that are used to help identify severe weather. GOES-R went up in 2016. That's GOES 16. We're now GOES 19 was launched in 2025 and went operational in 2026. So this was a family of 4 satellites. They're expected to be operational until 2036, so for another 10 years. The effort to describe the capability of the next generation satellites is already underway. Actually, it was underway uh, before GOES 16 went on orbit in 2016. So let's eh, I'm having trouble getting to the video, so we won't play that game tonight. All of the links that are in here have been checked today. Um, we get views. So uh, that was unenlightening. Why did that not work? Ah, okay. So in general, when we're looking at the various satellites, we can looking at the map here. If we go full disk, which is one of the products off of the GOES satellites, this view is generated once every 10 minutes. So the entire Earth, the resolution on the image as it comes down from the bird is 1 kilometer. So that's a tremendous amount of data. And you can see the United States. I'm kind of moving things around, but I'll move it to the center. You can see roughly where North America is right there. The GOES East bird looking, that was image from GOES East. This is looking at the continental United States. GOES does not detect the city lighting that you see. I took this image about an hour ago, so we were starting to see darkness on the East Coast. That information comes from other satellites and then is superimposed. So when you see the big satellites and they've got the night image with the cities on there, or you can see the cities, that's a composite image. That's not exclusively how it comes from the satellite. Plus the map image on the background is also an overlay. As we bring it down to tighter, we can see the Rockies, and here's Colorado. I'll move it to the center. And you can tell about an hour ago, the state was almost completely covered in clouds. So let's go back to, okay, you have to be smarter than the equipment that you're working with. And sometimes I'm not so sure that I qualify. Let's try this again. Ah, there we go. Had to find the right thing to click on. So our weather models, there's the NAM, the North American Mesoscale Forecast. It's run 4 times a day. Uh, the Rapid Refresh, which I think has been replaced by the High Resolution Rapid Refresh. And then the WRF, which is Weather Research and Forecasting Advanced Research Models. So when we talk about model grids, uh, the RAP runs at a 3 kilometer grid or a 13 kilometer grid. The high resolution rapid refresh runs on a 3 kilometer grid, so roughly 2 miles. Uh, the Get an idea of the grid size. Our runway at our home airport's 3,800 feet, so about 1.2 kilometers. So that it would fall completely within a grid when you were looking at making forecasts. When I talk about grids, one way to look at it, you have a horizontal grid, which is a map. You can see the grid laid out on the globe horizontally on the map or on the continents there. And then there's a vertical grid component that is based on atmosphere pressure, so height. And it's finer grid or finer resolution low down and lower resolution as you get high, excuse me, as you get higher. And you can see the kinds of things, we're looking for in the atmosphere: moisture, the clouds, the heating on the ground, the moisture coming off the oceans, the heating, the solar radiation, all the reflections, all of those kind of things. These are the things. But the key to remember is that this is three-dimensional. Most of the time when you hear it's a 1, 2, 3, 4, or 12-kilometer grid, what they're talking about is the horizontal grid, not the vertical grid. The vertical grid, like I said, is divided by altitude. In Colorado, we have one of the things that the model can do, this modeling can do for us, is we only have a few, very few, like 2 sites for radiosondes in Colorado. However, with the model, we can go and do point forecasts to create a virtual radiosonde for each of these sites that I've got marked, which is what we've done, or what some of the folks have done with the modeling. And then using that, they can create the weather products for those locations. So one of the things that the modeling allows us to do is it allows us to look at areas that don't have direct observation and use that information and use that to develop decent forecasts for those areas. So, and when I say virtual, it can be seen but doesn't physically exist. So there's no radiosonde launch at the sites that have stars on them. For the weather forecast models, BlipMap and RASP. This was the original work done by Dr. Jack, and then that was BlipMap, and then evolved into the regional system, which was RASP. And then those are free. And then the subscription, Top Meteo and SkySight. I'm not attempting to make an exhaustive list. I have talked to people from both of these organizations. SkySight, at least in the US, seems to be the dominant one. And, Matthew shows up at the convention and he's willing to stand there and talk to you if you've got questions. So I think, to some extent that's worth it. The early forecast models, like I said, BlipMap, so boundary layer information prediction map, and RASP, regional atmospheric soaring prediction. The difference between these two, BlipMap was originally run on a central server, and then you logged in and downloaded your products. And then RASP, folks at regional locations, it's like Dave Leonard did for the Front Range of Colorado, were running the model in their location so that it wasn't a centralized model that then had to account for everything. They could share the workload and get the product out a little faster. And so that worked out nicely. When we look at soaring parameters, here's a list of some of the parameters that Dr. Jack started with. So thermal updraft velocity, buoyancy shear ratio. So that's actually a composite of several things. You can go down through the list, but you can see the critical height, the thermaling for the top of the thermals, something that would develop overdevelopment. So some of these parameters are defined from the input source models. So this is additional processing on the output of the input source models. Some parameters are presented directly from the source model. For instance, the last parameter on there, CAPE, that's the convective available potential energy. That comes directly from the National Weather Service models. And then some of the parameters are composite. They're combined from factors in the blip map processing. So you can see the ones I have marked as composites on there. One of the things that he discovered, that Dr. Jack discovered, was he could also predict wave systems. He's, you know, he was located on the coast of California, and with the coastal ranges or the ranges just a little bit inland from the coast, they started looking for this phenomenon, and he identified it, and then somebody went out and flew it and found it and said, yeah, hey, this works. The other one that this also gave us insight to, which we didn't have before, were convergence lines. So basically, this is where we have two air masses coming together with winds blowing from different directions. And so the idea was, could we identify it and could we predict where it was going to go? The thing to keep in mind when you're looking at all of this is no single parameter forecasts everything. You know, we're not going to get a prediction from one thing. So what you can do though is you can take a look at the parameters. Some of them can be used to cross-check each other. We're going to go through parameters in more detail here in a little bit, and I'll talk about some of those relationships. And the parameters can be combined to give a better understanding. And even though we're going to look at some of this, I'm not going to do every one of the parameters that are available. I'm just going to do the major ones that we play with. RASP versus SkySight. I'm going to spend most of my time on SkySight. This is probably the last time I'll mention RASP tonight. It's weather forecast only, so it's today plus 2 days. It has an older user interface. Uh, it doesn't mean that it's not usable, but you've got to have someone in your regional area that is doing the processing for you to have access to it. SkySight is a worldwide product. Uh, they're attempting to do a weather forecast today plus 6 days. Like I said earlier, for micro scale, anything out beyond about 3 days is somewhat questionable. So they can give you an idea, but you know, don't bet on it. Too much changes between now and then. It does have an improved user interface. It helps with flight planning, route forecasts, and point forecasts, and we will be playing with that uh, as we go through the demo. Now, one of the things as we go into this demo, I'm going to be talking about the parameters. I'm going to be showing them to you. The slide deck, uh, I'll skip ahead a couple of slides and then I'm going to come back here. In the slide deck, I have every one of the parameters I talk about. I have pulled the help description and put it in the slide deck for all of the parameters that I'm going to talk about. But what I'm going to be doing is I'm going to pull up SkySight and then we're going to be running SkySight while I'm talking about those parameters. So you don't have to be trying to screenshot everything. All of this data is available in SkySight, but I've got it on the slides. So if you download the slide deck, you can sit there and look at that and then look at what you've got on your screen. Okay. So now let's see if I can switch again. Oh, come on. Sorry, I'm playing with the mouse in the background. And so, no, that didn't do it. Ah, there we go. Well, there we were. I wonder what happened. That's better. Okay. So this is SkySight, and So now comes the fun part. So this is a subscription service. It runs on the network. You don't have to install software on your computer. It runs in a web browser. You have settings over here on the top right, and so you can tell it where you are. So for instance, in my case, I'm telling it I'm in North America, US, Canada, and West. The United States, main CONUS is divided into two groups. The forecast model is pretty good on the western portion. It's pretty good on the eastern portion and the middle of the country. Um, it's pretty good, but it's better on, for instance, we got pretty good forecasting in the Rocky Mountain region, but if I were in eastern Kansas, I'd probably be uh, little less helpful, I guess. The other thing that you're going to do with this is you're going to go in with your aircraft and you're going to select the type of aircraft you're working with. You can customize it for the units that you want to use for the default. And then you also, when you go in for the, uh, scroll down, and in your account setting, you are going to set that you're a sailplane or whatever you were, and you're going to set your pilot factor. And the 100 in this setting is a Ventus 2 at 18 meters at 45 kilograms per square meter. So if you're flying something else, you have to adjust this number. I fly an SH-26. I will show you how to do this a little later. And then at the end of the presentation, I have a chart that has the gliders that are common at my club. It shows the formula for calculating this number, and that slide has a link to the OLC handicap list because that's how you're going to calculate it is you're going to get the handicap for your glider. So when we get down to the last or next to the last slide in the presentation, I'll go through that on how to derive this number so that when you have it in there, you are working with, uh, what you're working with is giving you information about your glider. Okay, hang on. Since I was playing in the settings menu, it said, oh, I've got to reload. And so that's what was happening there. Okay, we come over here. We have a couple of thermal overview uh, presentations. So this is called the potential flight distance. And basically you get on this for a day and you look at it and it says, for instance, let's see, oh, right here, this area right in here, um, that's a yellow. So we go over here to the chart and that says if I might be able to do something between 545 and 644 kilometers if I stayed in that yellow region. So I guess I could zoom back and forth, you know. Uh, this time of year, okay, this is today's forecast at 3 o'clock. Um, so, you know, on midsummer days, this thing's going to be yellows and reds and, now the whole thing about this is the distance that you could expect to fly if you took off at first thermal and landed at the last thermal using, McCready theory for the strong conditions and much slower in the weak conditions. And then this is adjusted by that pilot factor number, which the glider slash pilot factor number. So if you're 126, this would look a whole lot different than if you're a brand new Ventus 3. Okay, and this is one of those composite representatives. So this uses the thermaling height that's adjusted for wind speeds, and then it's also looking at the cumulus potential for this, and then it's modified by the buoyancy shear ratio. So there's a lot of work that's being done in the background on this slide to give you, or on this particular parameter to give you a feel of where you might want to go. Now, notice there are question marks. There's little question marks and there's big question marks. One of the things that's done in SkySight is there's this concept of ensemble models. So when I'm doing modeling, one of the things that I can do is I've got the output of my model, or in this case, the SkySight model. But then if I went and took a bunch of other weather models and ran them, and maybe time sequenced them or I adjusted them for different temperatures than what my model assumed or different winds or that kind of thing. But then I can run these and get a prediction out of those models and then take this ensemble and compare it. For instance, this is what they're doing in SkySight is they're taking that ensemble set and comparing those results to SkySight. And where it deviates, where these two items in the comparison deviate from each other, they've put an uncertainty factor. So that's the question marks that you find when you look at a chart in SkySight. If the question marks are small, then there's a relatively small deviation between the two sets of data. If the question marks are large, like they are over here, then that means they're probably not even talking in the same space, you know. So the nice thing about this is that it does give you some kind of quality indicator as to how well the models are agreeing on their predictions for this day for this particular parameter. Now, this is a very nice where do I go kind of tool, but especially during the high soaring season, if you're only going if you're going to stay with, let's say, within a 500K out and return, basically it's going to give you some confidence that I can pretty much go wherever I want, or there's one, two, or three major corridors that are going to work better than somewhere else. So this is a nice place to start your look when you're looking on a particular day. It doesn't mean that you would plan on this. You would do your planning directed on this, but this would give you an idea as to which directions you might like to go play. The next one, that's an overview, is a cross-country speed. And basically, what this one's doing is it's letting you say, this is, again, remember I said this is 3 o'clock, so 1500, so this afternoon. And there was some active areas down here in the southern part of the state. So this was saying, if you were down there and you were running and that actually was lift, you might be able to run. This is indicating somewhere between 140 and 160 kilometers an hour. But this is a snapshot version. If I go up here and I move it back to 2 o'clock, that changes. If I move it out to 4 o'clock, that changes. Okay. So this one is more time dependent, but this gives you an idea. And remember, I said you can correlate between different parameters. One of the things that you might correlate this one with is with the convergence parameter. You might see a convergence line and this, or a ridge lift line, or maybe even a wave area. And this would give you an indication, if it lined up with it, it would give you an indication that there's a nice correlation between the different parts of this model. So you can bounce some of these parameters against each other, again, to help develop your confidence in what you're observing when you're looking at the model. When we start to talk about thermals, the thermal parameters, so we have a thermal strength forecast. So in this case, if there were thermals out there at 3 o'clock this afternoon, you can see the color over here on the right-hand side. So that's the relative strength. So this yellow is, saying, oh, there might have been 5 knots worth of lift out there if there was lift. Okay. Notice the stippled area. That is an indication that the buoyancy shear ratio is going to decrease the available lift. And notice down in this portion that that stippling is really, really heavy. And that generally would indicate that it might not even be soarable there because it's getting so torn up. The blue areas are indications that there's moisture. So we're we were expecting to see some moisture up in the mountains this afternoon and some out here on the plains, which we did see some of. Now, the nice thing about this is, again, in the summertime, especially once we get past the early spring thunderstorm season, is this will give you a decent indication of the direction you might want to go, again, comparing back to that possible distance. Now, remember that the potential distance, though, is talking about if you started with the first thermal at 10 o'clock in the morning and stayed out to that last thermal at 7 o'clock in the evening, and this being, mid-June to late July kind of time frame. So, and one of the things that SkySight does is you notice there's some numbers next to my cursor. So wherever that cursor pointer is, it's giving you the numeric value so you don't have to try to keep balancing the colors over here and going over to the chart and saying which one is it. You can just drag your cursor around and it'll fill in the number for you. Of course, if we're going to talk about thermal strength, we want to talk about thermal height. And no, I have no idea what that dark line is up there. That's an artifact of something in the model run. Let's switch it back to 2 o'clock and see if it goes away. Yep, it went away. So there was something in the model run at 3 o'clock that was generating that. Now, on this chart, this is the height above sea level, so MSL. Again, notice that I've got the number on my right next to my cursor. So 16,000 feet there, 11.5 there. Notice that we've got storms and it's saying 6,500 feet, which is ground level, maybe even a little below. Yeah, remember, I'm in Colorado. The lowest point in Colorado is down in a river valley where it crosses into Kansas, and that's still 4,500 feet above sea level. So this is this is the height that is predicted here. This is when the lift drops to that magic number of 175 feet per minute on the lift. Now, the RASP system had both 175 feet and 225 feet. And I always like to use the 225 feet just simply because, I was flying gliders that their minimum sink was generally less than, uh, 225 feet. So if you're flying, depending on the glider that you're flying, it might be possible to get this high, and then it might not be. Now, here's the other one that's kind of interesting. It goes along with this is a height of thermals AGL. Okay, this is the depth of the thermals. So how high does the thermal, not above sea level, but above the ground? And where this is important when you're doing your planning is because this gives you some insight for a starting point when you're looking at your initial height band estimates. So for instance, if we were out here today and it said that the top of the thermal was going to be 12.5 AGL and the terrain out about where that cursor is about 5,500. So, uh, that means that theoretically it could get to 17. It's not going to get to 17, but that's okay for this time of year. But what that does is if you wanted to say, okay, I'm going to do 3 height bands, the top one, run like you stole it, the middle one, um, take lift when you feel like you need it, and the bottom one, take any lift you can find, maybe divide it evenly by 3 and get your 3 bands. This gives you a starting point, uh, especially if you looked at this number around your launch time and for your local airport to give you a feel of, am I going to feel comfortable getting away? And of course, then your first thermal is going to help you start to calibrate yourself. So you're going to move from this guess on the ground to a calibration based on your observation, and then you're going to build your mental model during the day. But what this parameter does when you're using it in SkySight is it helps you get a start on that work. Notice this is indicating moisture, rain, and let me look a little further. Uh, Unfortunately, let me back up time a little bit. I had something I wanted to show you, but it's not showing up. All right. The other thing that it will show you is if the storm is predicted. Remember, we're talking about predictions here. If the storm is if this rainstorm right here was predicted to have lightning, then as let's zoom in on it some, you can see uh, the area where they're saying there's no lift. This thing is likely, you can see if you look closely at the symbol, the symbol's still shrinking, I'm sorry. If you look closely at the symbol, you can see there's little raindrops in the middle of it. And if the storm was likely to develop into cumulonimbus, and it would have lightning symbols around the areas that they thought the lightning was going to be. So they were trying to do also a lightning prediction would show up on this. And then here's another one. They call this one significant weather. So uh, probably no clouds out here, some clouds building where they're partial and white. Partially overcast as it goes dark. It's definitely overcast. And then in this case, we're going to zoom in right here. This case, you can see the uh, idea of lightning. So, here's the primary influence of the storm. That's probably the main rain shafts coming down and the lightning around that area. Okay. So you can see this stuff in the predictions. And so if this were a bright sunny day and I saw that, I would say, maybe I don't need to be over here at 3 o'clock in the afternoon. Now we're going to shift off to clouds. One of the things that SkySight added, I think they added it last year, but it's still marked as new. This is the cumulus overview chart. And so it's combining data from several of these um, other parameters. We'll look at these individually here in a moment. But the goal with this one was to give an overview so that you didn't have to look at these individually and then try to synthesize this information in your brain. So they've combined several of these parameters. And what you'll find here is this is the likely distribution of cumulus clouds represented in the dots. The tighter groupings, the clumping, says increasingly thick and perhaps overdeveloped. You can still see that they're keeping the rain indication on there. The gray out here, that's showing mid to high level cloud coverage. So we're talking about the overall cloud coverage. And then if you've got soft color in the background, then that's probably the heights of dry thermals. Nice little composite chart. Um, Again, gives you an indication, and again, this is time sequenced, so you can see the evolution. I'm going back earlier in the day, or go a little later in the day. So you can start to see some of this is dissipating already at 4 o'clock. I'm gonna put it back on 3 o'clock. Matter of fact, it dissipated a lot. Cumulus depth. So this is the difference between the top of the predicted thermals and the condensation level. So, are you going to run out of lift before you get to the clouds? And then the cloud bases. So the top of the predicted thermal and the condensation level, or cloud base, I'm sorry. So where the cumulus is expected to form, what is the height of that above sea level? And gray. So this is saying, for instance, up in here, it was saying that cloud bases should be around 13,000, and the gray is saying not as much certainty that there will be clouds, but you might expect to find clouds in that gray area. Now, the cumulus coverage. So you're starting to see with these last three parameters, you're starting to see the this is the underlying information under this overview chart so that you don't have to try to pull all this data together on your own. So percentage of sky coverage. So notice the colors now over here on the right-hand side are percentages. These are all percentages now. Basically, um, something like about a 30% coverage is probably pretty good for having clouds that are working. If you get above 70, 75%, it might not be soarable, or it'll be flyable, but you may not have any usable lift because it's cut off the energy source to the ground. And then the cloud cover. In this case, the colors are talking about height bands. So a low, which is the blue, so those are clouds in the first 4,000 meters or the first 13,000 feet. Medium is between uh, 4 and 8, and the high, which is the red, is the high clouds. Those are above 18,000 feet. This is one that is overlaid. If you're in an area where you have thunderstorms, then CAPE, convective available potential energy. This is the thing that the National Weather Service, and most of the time, CAPE is brought through directly without any processing in the soaring models. I don't know if SkySight does or not, but I know that Dr. Jack's models just brought this one through totally on its own. Uh, Once the CAPE level gets above a certain level, this is one of their key predictors for thunderstorms. So in this particular one, um, it's not a particularly active day, but there is sufficient convection uh, to support these rain showers. And then this is a prediction. So for 3 o'clock, this is a prediction of how much rain accumulated in these areas. Notice we're in millimeters over here on the side. By the way, if you ever want to change, no, that one won't change. This is always in millimeters. But if you ever want to change the scale on the side, try clicking the units indicator up here, and you may be able to get a different representation if that's what you want. But what this is saying as a prediction is at 3 o'clock, these areas were likely to have somewhere between a half millimeter and let's see, this one's got yellow in there, somewhere between a half millimeter and 3 millimeter in this particular area right here. Okay, so this is saying not what the rain is going to be at 3 o'clock. This is predicting with everything that it saw how much rain fell in that area in the last half hour. Might be an indicator as to whether or not, for instance, let's say you managed to get back out in the sunshine, but you've had, you know, 3 to 10 millimeters of rain on that ground, it's probably not going to be hot enough to generate any thermals. So just some ideas for planning purposes. Let's wander off into wind. So you can put your wind presentation on screen with different representations. So I put it on with wind barbs. I'm still showing the rain. Uh, I'm still showing the rain category. Or you could put it on with streams. And I'm not going to hang on this one too long. It takes it a while to develop all the streams, but this will actually put a little motion stream on there. Or you can turn the wind presentation off and just look at the data. Remember I talked about surface wind. So here's surface wind with barbs. Let's see if I can, yeah, if you look carefully at the screen, I'm going to zoom in I'm going to zoom in up here because it's actually got a nice phenomenon going there. Let's fill it in. So you can see what looks like some convergence right here, but now it's coming in real nice and clearly. So there might be convergence line right here. Well, if we went back and look at the clouds, we also might find a prediction for clouds right there as well. Okay. So you can use the wind streams or the barbs, or you can turn that off and just look at what it says the winds are going to be. So for instance, you see this curl right here? That is probably a thunderstorm. That curl indicates that there's a swirl right there, localized low pressure. That's probably a thunderstorm. In the summertime, what you'll see, oh yeah, we got one right here. See the ring forming right here? That would generally indicate that there's a storm right here, and what you're looking at is the outflow pattern coming out. And there's another one down here, right here. Okay, so remember, I said it with the models. The model data is the picture on the screen. Now what you're hearing from me is interpretation. Again, we have something that looks like it's a developing ring or a dispersing ring right here and right here. So if this were a summer day, this line of term points that are out here, this is I-70. So uh, 50 miles east from the airport, 45 nautical miles east from the airport is where this dot is. That's Lyman. So I wouldn't necessarily, if I were looking at this, I would say if this was showing me this is 3 o'clock, so this is anywhere from 3 to 6 o'clock, I might say in my planning, I don't think I want to be down here at that time because my experience has shown me that this is probably telling me that those are fairly active storms and those are outflow boundaries. Now, this is the surface wind. So this is 10 meters above the ground. Okay, so this is what you would see when you were on the ground. If you were looking at your airport at 3 o'clock, so let's zoom in down here. Let's go back over here. This is the area where, there we are. I've got the AWAS station marked on the airport. So here's the winds. Let's throw the barbs on there. So the wind's out of the south at the surface. So at the 10-meter level, at somewhere 5 to 15 southwest uh, to south the further north you go, and more from the west the further south you go. Notice the outflow around this right here. You can see that circle. So if I come back out a little bit, we don't see a really, we got a pretty good defined boundary out here, and you can see that the winds are all coming out from right there. But they're still only about 15 miles an hour or 15 knots. So that wouldn't be too bad. But for 3 o'clock in the afternoon, that would tell you if you were coming back into the airport, expect south winds. The thermal layer, this is speed and direction averaged over the height of the boundary layer, the active boundary layer. The boundary layer on any given day is going to vary in its depth, how high it goes, and it is the convective layer. It's the layer that's being affected by the convective activity. So the speed and direction for the boundary layer is averaged over the boundary layer. If so that's saying, that's showing that same outflow a little faster, 15 to 20 knots, that kind of thing. Let's go back out here by Lyman and see by, so this doesn't look anywhere near as bad as you get up into the boundary layer as what it looked at the surface level. But you can see right here, that's kind of interesting. And notice, we're into 25, 30, 35 knots looking at the wind barbs. Okay. Again, if you're planning purposes and you saw that, that says, that's somewhere I probably don't want to be around 3 o'clock. Now, remember, all of this is prediction. So you're planning you're planning your flight this afternoon based on these predictions. Even if you have this readout in the cockpit of your plane and it gets updated, and SkySight updates, I think at a minimum of every 6 hours. It might be more rapid, but I think it's on a 6 hour refresh cycle. So even if you were downloading this in the cockpit, this is still a prediction. It's not an actual observation. So you still have to look outside. You just can't lock onto your screen. Okay. Now, one of the problems that you have with this is that since this might conceptually be talking about a layer of the atmosphere that is 10,000 feet deep, one number, that if the atmosphere's got some supporting, like frontal passage and stuff like that, if there's a large change in the wind direction through the boundary layer, uh, this might not be, this one value right here saying 35 knots right there. Uh, if we went back to the surface, it was 30 on the surface. Okay. But we'll go to the top of the boundary layer and it's 25. Okay. So this one number right in, that's averaging all the values through the boundary in the modeling through the boundary layer, that could be somewhat misleading. There can be localized little pockets that will be very different. Thermal or the wind at the top of the thermal, so at the top of the boundary layer. Now we start to get into some of the interesting things. Maximum up and down motion within the thermal layer as convergence line as created by the moving air masses. Now let's go back up here. Remember when we were looking up here earlier, we were seeing uh, some interesting wind flow. Let's go back over here, turn the streams back on, and let that build for a few seconds. And remember I said, it looked like something was happening right there. Okay, now let's watch this line right there. Let's turn the convergence on. Gee, lines up. Notice that the wind barbs are coming into this region from different directions. Okay, that's also an indicator that there may be convergence somewhere. Okay, convergence is a wonderful little phenomenon because if you can get into it, you can run in a straight line for miles and miles and miles. I had a flight in the summer of 2024 that I did 90 miles in a straight line without turning because I found a nice, comfortable convergence line and I ran my speed up to the point that my sink from my speed matched the lift I was getting in the convergence line. And like I say, I ran 90 nautical miles without turning. So convergence lines are magic. Want to go fast cross country? Find your convergence lines. Forget thermaling and then diving at 120 knots. Find the convergence lines or the energy lines. Okay. Now let's zoom back out. Notice that we're going to see some convergence lines back over here in the mountains. So let's go back to our wind and notice that the winds are following the shape of the mountains. The convergence lines are starting to confirm that. And then if we go to the next one, ridge lift, you can see the ridge lift lining up on those mountain chains. So you could use that as a prediction tool. However, remember, ridge lift is in the laminar flow area right on the obstruction. So that means being close to the terrain. You wouldn't want to be real close to the terrain up here. This might not be too bad because you got a valley you can fall off into, or right in here you have a valley you can fall off into. But if you're working ridge lift, you've also got to be very aware of the terrain around you. So my comment down here at the bottom, for complex wind profile, no single number is an adequate descriptor. I also just showed you that the wind diagram, the convergence diagram, wedge lift diagram could be used to support the idea of that might be a good place to be or that might be a good place to stay away from. Now, it has its own section, and this is the wave area. Oops. So we can get, there we go. Come on. There you go. So the wave, this is an attempt to identify possible locations for wave. We're constantly used to calling it mountain wave. Meteorologically, it's called a gravity wave, and it is the response of the atmospheric flow to some type of an obstruction. Now, when it's mountain wave, it's real obvious. It's a line of mountains that are sticking up out of the ground. But if you go down to West Texas into the canyon lands in West Texas, that obstruction that perturbates the flow of the wind is the canyons. It comes over the edge of the canyon, drops down into the canyon, and then rebounds and creates wave in the canyon or coming out of the canyon area. That's why the guys down there can, get their diamond altitudes. And there's no mountains around, but they're flying in wave. The other thing that can cause wave is weather patterns. So convergence lines. See the convergence line we were looking at up here? Okay. Is that wave? Is it convergence? We know it's not ridge lift. Okay. But you can also use convergence and wave to help you wave forecast because the phenomenon can look very similar. There are conditions where the cloud itself, a wall of clouds, in addition to generating a convergence line, it can also generate ridge lift off of the cloud, and the clouds can, if they're the right height and the right density, can actually be sufficient obstruction to the flow of air that they actually can set up wave on the downwind side of the clouds. So you could have ridge lift on the front side, convergence lift, converting to ridge lift, and if you could go over to the top and find wave on the backside. I'm not recommending that at all because, what happens if you're on top and everything falls apart, right? Okay. So this also shows you that you can take a look at this stuff and go, oh, uh, this might corroborate convergence in these areas. This also, notice the flows, the arc right here. That could be the result of the outflow boundary from the storm. You can see the one I pointed out earlier down here as well. Okay. One of the tools that they have is they have the ability to give you something that will let you examine the predicted, if you wanted to make a flight across a wave system or within a wave system, you can select the wave cross section. Let's come up here and pick a spot and draw a line down through. Oh, I'm going to carry it over here because let's carry it up here to this little section. Now, what's going to happen is I'm going to put it over here. Notice we got an airplane or we got a glider symbol. This is that slice looking at the lift through that slice. And as I move the glider across, you can see it improving over here or it getting worse or, you know. So you can use this to help you traverse wave systems, which I think is really interesting because sometimes, especially in uh, the later spring and into the fall, the mountains that are west of us will set up wave systems that if you could get into them, you might be able to run 50 to 100 miles without having to turn and modulate yourself in and out of the wave in order to control your altitude. And then the red X up here takes you out of this little out of that tool. They have another tool down here at the bottom called the 3D wave. This is a visualization tool and it's cute, but I can't get anything out of that that helps me plan other than it does give me a little, a slightly different representation of where the lift and the sink would be. But I really don't see, like I say, it's interesting, but I don't see it as a planning tool. Now, the other one, the vertical velocities. And so vertical velocity at 3,000 feet means absolutely nothing in the part of the country I'm in because, like I said, the lowest point in Colorado is down at the border with Kansas at 4,300 feet or 4,500 feet. So let's bring it up to 7,000 feet. Notice I'm not getting anything back here in the mountains because that's all above 7,000 feet. So it's breaking into 10,000. We start to see useful information back here. It's getting more useful for the front range. Um, I don't usually, I fly out of an airport at 7,000 feet above sea level for its field elevation, and we have 10,000 feet mountains 15 miles to our west. So I start getting interested at about 13,000 feet, and we'll take it up to 16,000 feet. Interestingly enough, this looks very much, the meteorologists would call this a zonal flow because if it's large enough, it flows from one time straight from one time zone through to the next time zone. But this is a fair amount of west wind, but it's this is at 16,000 feet and 20,000 feet. Notice it's petering out. So what that tells you is that the atmosphere itself, the various things that contribute to wave one is a stable atmosphere, and so that's saying that the atmosphere is not stable enough for the standing waves to stabilize. So we've got too much other stuff happening. And with the rain showers and stuff that we were seeing today, I'm guessing we've got too much convergence to actually set up a good wave based on the mountains. What we're seeing is we're seeing lines of indications based on the storms out here and the air patterns and how they're behaving around them. Okay, now there are some general interest parameter forecasts. SkySight has added a glide range uh, forecast tool. It's going to take it a few seconds. I'm going to zoom in some and maybe it'll come in a little faster. And notice that what this has done is I'm going to zoom in a little more just to make it a little more obvious. It's giving us range rings and potential routings to get from this location to in this case, the Lyman Municipal Airport. And it's saying right here that the required altitude is 9,029 feet. All right. This is basically a guide, terrain aware glide range map. So these areas that you see are either, uh, yeah, most of these I've marked they're either landing points or they're waypoints. Uh, but so showing safe landable area, and it's using a 22-to-1 glide ratio multiplied by the pilot glider factor, and it's working to maintain a 100-meter terrain clearance and a 250-meter arrival height. And so notice that right here, it's showing that I should follow a curved course, whereas down here, it's showing I should follow almost a straight course to get up to Lyman. I don't know what it's going to show from up here. Oh, it's going to take me to Miglo. So notice that the colors, so if I'm in the green up here, lighter green here, it's going to send me up to Metro Grow. If I'm in the yellow right here, it's going to send me to High Plains. And if I get into this color, it's going to send me to Lyman once it gets a solution. Okay. So this is a fairly new tool, and I think it's interesting. I mean, it does give you something to look at for the day. The next one I want to put up here is the wind shear chart. And this is the difference between the wind at the top and the bottom of the thermal layer. And it's not telling you the direction of the shear, but it is telling you the magnitude of the shear. So like when we're over here, right around Lyman, that's 24 knot difference between the lowest portion of the boundary, the active boundary layer, and the top portion of the boundary layer. Whereas if I go further west, it's only 5 knots. But up here, it's 26. Okay. What this does is this gives you a little bit of a measure of how active horizontally the winds are and the fact that they are varying in strength. Um, so that may give you an indication of how well you're going to be able to climb. And then there's another one down here. This one uh, is very interesting. Let's come back over to the mountains. Let's go down here. Uh, ah, this will be a good example right here. Okay, so this is Salida, Colorado. It's back in the uh, mountains, and this is the Arkansas River Valley coming down. This is the uh, uh, Collegiates, or no, this is Sangre de Cristo. Sorry, Sangre de Cristo. And what it's attempting to do is it's attempting to show you the mountain winds. This is not telling you the lift. This is telling you what is the predicted winds uh, if you were in that valley trying to traverse the valley. It's this is new, not real new, but this is new. SkySight is working on a version of this to overlay this wind information with the glide range information. And they have experimentally they have it working in some segments of the Alps. And the genesis for trying to pull this together is there was an accident a while back that uh, they couldn't figure out why they didn't make it to the airport. They ended up putting it down some distance away from the airport. So, and yeah, there's the Salida Airport. And what it turned out is when you looked at the winds, notice that like in this case, we've got winds as a tailwind pushing us up the valley, but all of a sudden now we've got crosswinds. In the example that they were looking at, that again challenged them to look at putting this together with the glide range. One of the things that happened is as they came up the valley, this tailwind and crosswind turned into a headwind, and it knocked them down hard enough that they couldn't make it all the way back to the field. It's going to be a while because this is compute intensive, and we have such a huge area in the United States that with this kind of a tool would apply to. So it will be a while before that combined tool makes it to the United States. But again, from a planning tool, I liked this. I saw this and I liked it, and I went, yeah, that could be interesting. It could be useful. It might give you an indication because this is talking about down in the valley. So this might be a case of, you know, where you might be willing to go into the valley, but this indicates that's probably not a good place to be. And that's just as much a part of your planning as anything. Okay, so I've talked about the parameters and have given you some interpretations of how I look at it, how I would use it. Let's come back out here. Where am I? Okay, I'm in the southern part of the state. Now, another tool that was added in the last year or so is called the point windgram. So I'm going to put this real close to my home airport. And what this is doing is this is looking for that location. This is looking through the day at what this what may what's going to happen. So we've got the start of lift. You can see the lift starting, you know, and down close to the ground, it's not really kicking off till about 10 o'clock, but you get up a little higher, not even 7,000 feet or 1,000 feet AGL. And the lift is already mildly starting at 9 in the morning, and look out here at about 9:30, get over here to about 10 o'clock. And if you did a 2,000-foot tow, which puts you up here, you should have 2, 3, 4 knots, 5 knots, increasing through the day to 6 in the middle of the day. Maybe notice that the clouds come in, and so it probably cuts off some of the lift. We can see it drop off. Some of them move out and it improves and then drops off for the end of the day. Okay, so this gives you a feel. So what you've got is the black line is the boundary layer. So notice as the day heats, the boundary layer goes up. And the condensation level is the pink line, which may not show very well on your screen. It's just barely visible on mine. And notice up here, it's below the, here you can see the clouds forming. And then the gray, this is cloud cover. And so what this is telling us is starting at about 12:30 and running on into the afternoon that we have anywhere from uh, 15% to 90 to 100% cloud cover and then it fading off again. You can uh, squeeze this down. So here's looking at one day, here's looking at the next day, and then there's the third day out there. Okay. So that allows you, for instance, to take a look at, what's it going to take to get out of the airport? Um, you know, wow, could I really get to 18,000 or 16,000 feet over the airport? But tomorrow, gee, I'm going to be lucky to get 3 knots and be at 8,000 feet. So 1,000 feet over the airport. Because remember, I said my airport's at 7,000 feet above sea level. So this gives you the ability to look. Here's the overview. You've got other things that you can look at, but you could look at this at the airports along your flight route. So this gives you a point solution. The other one, and this one's been around for a long time, is the route forecast. And route forecast works in two different ways for you. Okay, I'm going to click real close to my home airport. And you notice that it's populating things up at the top. Today's a lousy day, so that's probably not going to be too good. I may have to go back to yesterday or maybe the day before. Ah, there we go. Okay. So it is predicting tasks. Green means a relatively short task. You might only be out for a couple of hours. Yellow means a longer task. So this doesn't tie to uh, FAI badge distances or anything like that. This is doing durations of the tasks. So green is a relatively short task. I mean, like this one, it's calling for 44-kilometer out and return at 132 kilometers an hour. Okay, so I'm only out there for 20 minutes. Okay, all right. Um, Here's a 500-kilometer straight out. So at 138 kilometers. So for today, a this would be a little more than a medium task. This would be a hard task. The red is the challenge task. This is in their coordinate system. This is the I'm going along on the longest potential flight distance, first thermal to very last thermal, maybe landing a half hour before sunset on my final glide, that kind of thing. Okay. And that's the general definition for the colors. And if you, let me scoot the map out a little bit. And so there's that out and return, that's an out and return, that's an out and return. There's a straight out. Here's another straight out. Uh, Anybody adventuresome? 900K triangle? Not today. I mean, remember, when we're looking at this, this is a straight out, that's a straight out. Okay, this is the only one that's a triangle. Um, okay, so it's going to give you hints about where you could go based on what it sees for the day. Now, of course, again, you have to interpret this and say, is that a flight that I really want to make? The other place where this comes in handy is let's uh, let's say I want to do. Let's come up here. Is that last chance? Yep, that's last chance. And I'm going to come down here a ways. Let's pick Fox Valley. And now let's come home. And there's my task for the day. Okay, so there's a 300K triangle. Now, it's not an FAI triangle. You can see it's the software is going to help you. If I wanted an FAI triangle, I might be able to drag one point out here. Ooh, okay, now that's a 300K that's an FAI triangle. See, because I'm in all of the little indicators. All right. And across the top, it's going to give me, notice the glider moving along the line. So now I'm getting a thermal profile along that course line. Okay. Again, the hard black line is the boundary layer. Wow. Out by Lyman, it's down to the ground almost, all the way across. And the pink line is the convection condensation level, and then the clouds. Uh, and it's also going to tell you the thermal tops as you work across here. So there's tons of information, including the wind. And except today was not a day that we could make this flight, period. Let me back it up. Yesterday wasn't a bad day. I wonder if it would. Ah, okay. Here's a better example. Here's yesterday for this same flight. Notice it's a little more optimistic, except when I'm out here at that northwest corner, but doesn't look too bad otherwise. And notice that over here in the chart, it's giving me some uh, times that I can work with. And so I can say, I can go down this list of stuff over here, and I can go, all right, so this starts at 11:30 and finishes at 4:30, and I fly at 100 kilometers an hour. Let's go down this list and find the fastest time in the list. And now what it's done is it's showing me the flight. Here's 1400, 2 o'clock, and over here is roughly 1620, so 420. And it's showing me the conditions that I might expect to encounter while I'm making this flight. And notice the dark line in the middle. What it's doing is it's trying to optimize that flight for the conditions that it expects to see. So rather than flying it straight line, it's going to tell me I need to divert a little bit south. And so now we can come back to the other tools and look at the thermals. Not bad. Um, we can look at the clouds, and we had depictions of clouds up here, but still, okay, so there's going to be some cloud coverage. Maybe there's enough that the clouds are actually going to help, you know, let us know where the lift is. Um, let's see what the thermal layer winds were yesterday. Okay, predominantly northwest and basically 5 to 15. Okay. And so we'll have a headwind coming home. Let's see if the convergence shows up anything. No, the convergence didn't really show up anything lining up, although I might want to change my point out here so I could use this convergence line. Okay. So here's the planning tool for you. Now, neat thing about this planning tool is you can download it. Got a QR code for those of you that are using uh, Navigator, and you've got your device where you can use the camera, or you can create a task file that then you can load into your various devices. And especially if you were going to do you and a couple of friends, you might declare it to WeGuide so they can go download it from WeGuide, or again, there's the QR code for it. Awful lot of stuff. Okay. And Let's go back to screen two, and I'm looking for my slide. There it is. There you go. So that's I've shown you with the tool what you can do with the model-based forecasting, how it can help, and what the parameters are. Like I said, I've got slides with all of those parameters described using their help description for each one of them. So download the slide deck, use it when you go through it. Now, when we're using the model-based products, we can we can download to the cockpit computer. There'll be static images. Depending on the software that you have, you can download uh, the model forecast, say from 9 o'clock in the morning, and then it usually, the weather map usually replaces the terrain background, and then it can be time phased through the flight using a clock, using the clock intervals to bring up the display. So if it's updating, if the model could give you 15-minute updates, then you would get it on 15-minute intervals or half-hour intervals or something like that. Um, you got to remember that this is still just a prediction. And, if it's 3 o'clock in the afternoon and you took off at noon and you pulled the model run onto you did the download of the offline images so you could run it offline in your cockpit computer, you might have pulled a model that was run at 9 o'clock. Okay. What it is useful for is it's handy for hints, maybe over there, you know, maybe if I go 5 miles north, I'll find that convergence line. It is possible to bring these things in, especially in the ODN with the phone chip in it, or if you're running your software and you're using your cell phone as a hotspot. Uh, for instance, the Navigator software will allow you to bring in the convergence and the wave and the wind, I think the wind, as model updates in case there have been an update in the model run since you took off. You have to remember, though, that this is still just a prediction. The other thing is that you can get other weather information. So if you're looking at what might be real-time weather, for instance, you've got a FISB capability and you're getting the NexRad radar. Okay, you have to keep in mind that the data in the service is always delayed. Figure at least 15 minutes out of date, which means you're not going to use the stuff you're getting in your cockpit to thread your way through a squall line or around thunderstorms. You're going to be doing that looking outside. Even the National Weather Service radar, remember I said it was 10 minutes if it was nice and clear, and it was 5 minutes, but don't bet your life on that 5 minutes. It still could be 10 minutes out of date. One of the things that Navigator will let you do is if you're tied in with your SkySight account, is it will allow you to pull down the visible satellite image so that you can see the clouds. I've tried it a couple of times and I'm not real satisfied with it. I mean, if I look at it, like I was playing with it yesterday down at the club, I was working on my glider, and so I turned all of this stuff on and I was playing with it, and I brought up the cloud view, the satellite view, and I could walk out of the hangar and look and see the clouds were approximately where they were showing me on the image that I had just got downloaded to me. Um, and that could be useful, but it didn't tell me anything that I couldn't see just by looking out and saying, oh, I want to go to that cloud. And I did notice that, for instance, there was a real nice cloud that was over the airport, but and it was pretty good sized, but it was less than looking at it and seeing where I was on the airport, I estimated that it was really less than the runway length long. So it wasn't enough of a phenomenon that it was picked up in the 1 kilometer resolution of the image. So there, I had clouds that didn't show up as well as clouds that did because they were well formed and large. So when you're looking at using this material in a cockpit, even if you've got true real-time weather, expect it to be delayed. And even if the product looks neat when you're sitting on the ground, it might not be usable in the air. If it's derived from the model, so even if you've got SkySight and you've got the convergence model and that kind of thing, even if it's a model, that's still just a prediction. You have to keep that in mind. Okay, where'd it go? There it is. All right. What do I do? How do I do my simplified forecast? I start on Monday. A friend of mine calls it the picnic forecast. So look at the 5 to 7 day forecast on your local TV. I want to thank Dave Leonard for that little name for it. And if I'm going to look at it from the any of the planning tools, I'm going to look at 2 o'clock in the afternoon. So whether it's SkySight or whether it's RASP, I'll do a uh, potential flight distance, and I'll look at the lift and I'll look at the height, the strength and the height of the lift as far out as the model will allow. Tuesday and Wednesday, I do the same thing, but what I'm looking for, not so much absolute what it's going to be, I'm now looking for how it has changed from what I saw yesterday. And when I do that Tuesday and Wednesday, because this is going to give me an indication of how active the atmosphere is, how fast the large fronts are moving, and how fast the fronts that are below the threshold that National Weather's reporting. There's other things that are moving out there, but this gives me an idea of how volatile the overall uh, weather is, or is, as you know, and how the forecasts are evolving. Then on Thursday and Friday, I do it again. I'm looking for changes, but at this point, I start looking for my 3 possible flights. I pick three just convenient. Okay. Now, that's assuming I'm not flying Friday. If I'm flying Friday, then everything backs up a day. Okay. So this is assuming flying Saturday and Sunday. Um, so now I'm looking at my flying days. Saturday in the morning, so Saturday or Sunday morning, I'm uh, I'm usually looking at the models about 6:30 in the morning, and then I review the overall day. Uh, I want to start at 11 a.m. and look for out to 5 o'clock. And now I'm checking against my most likely flights, and then uh, I get out to the airport. We have a computer in our clubhouse that we can use to hit the weather models. And probably somewhere between 9:30 and 10 o'clock is when the last of the model runs that are going to be usable for you for the day is going to occur. Now I'm reviewing 9 o'clock to 5. If it's truly high summer, we've all gotten in the habit of being home by 5, but if it's truly high summer and it looks like a really neat flight, then let's run it out to 7 or 7:30. Of course, the last 25 miles might be final glide with no lift. I'm checking that against what I think is my likely flights, and I download the model data. Especially when I get back in the mountains, I don't necessarily have a good cell phone connection, so I can't depend on getting the model data or the real weather data back in there. So I download it and I load it onto my tablet and in the computer that I'm using in the cockpit. Normally, at least in our part of the country, it's sustainable by 11:30. It might not be cross-country worthy until sometime between 12:30 and 1:30, but that's okay too. But I've also gone out there and, taken, I'm usually a late launcher. I'm usually one that, you know, if we've got one tow plane. If there's six gliders ahead of me in the line, there's no reason to push out and spend an hour sitting out there waiting for them to launch so that I can launch. I'll stay back at the clubhouse and, have something cold to drink. And if it's afternoon, I may eat my sandwich and then I'll go out. But I've also launched, early and surprised myself and been on course by noon. So, uh, the whole goal behind this is to have fun. As we move down, we've got I've got something blocking my mouse. There's my mouse. Hi, mouse. How are you? There you go. Here's some of the acronyms that I've used tonight. Here's the chart that I promised you. So the SkySight pilot glider factor, is based off of the Ventus 2C at 18 meter. It has an OLC handicap of 119 and its pilot factor is 100. To compute your pilot factor, take the OLC handicap for your plane, divide it by 119, multiply it by 100. So my Ventus had a handicap of 112, so its pilot factor's 94. My ASH 26 has an OLC handicap of 118, so its pilot factor is 99. This is a sample of, I think a couple of them are gone now, but this is a sample of pretty much all the gliders that we have on our field. One of the things that you need to watch for is like the 126s and the 136. That's the pilot factor they have. I don't think the pilot glider factor, I'm sorry. I don't think it will go that low. So it will always be predicting more optimistic than your glider's performance. One of the things that I thought was interesting when I made this chart up, uh, OLC, the sacred cow plane for the OLC is the ASW 19. It's 100. And I always have categorized the Pegasus as being the French version of the 19, but it's got a OLC handicap of 102. So, and if you wonder what's going on with things like the JS3s and the Ventus 3s and those things, you can see uh, their OLC handicap's 122. So, anyway, and at this point, it's time for questions.
Dave, great job. I appreciate it. The only question we had was around the CU overview in SkySight and the red dots and
Uh-huh.
whether was it a radius of the cumulus? And I know the answer because I use that and it's just it just
It,
shows where the trigger area is,
that's
not the
right.
scale, right?
Yeah, it's not trying to quantify anything other than saying uh, a little bit here, a higher density here, high density over there, but it's not attempting to have the dot say that the cloud is any size. It's just saying likelihood of clouds and likelihood of concentration.
Perfect. That was the only question we had specific to your presentation tonight.
All righty. Well, in that case, everyone, as we come up on the, yeah, it wasn't too bad tonight. So next time, flight tracking. So we're going to be talking about uh, tracking our flights using tools on the ground so that we know where our folks went to make us all feel better and enjoy the flight while they're out flying, and what are the techniques and mechanisms that we have to do flight tracking. So April 23rd, 6 p.m. Y'all have a good one. Good night.